So, according to the law of conservation of energy, energy is neither created or destroyed. It is simply changed in its form. So the role of an electromechanical machine, like motors and generators, is to transmit energy across a system by converting it from one type of energy to another. So the first thing that I want us to look at is a simple electrical motor system. Okay. So on the left-hand side, which is going to be our input or source side, we are going to have an electrical system. And I'm just going to represent that by a large black box like so. So this will be our electrical system, which we are considering to be our source. And our electrical system is going to be connected to our motor. So these terminals here are what are allowing me to connect to my electrical motor, which I'm just going to represent as a circle with the letter M inside of it. We are going to have some voltage drop across the terminals of our motor, and I'm leaving this as a lowercase v. It could represent a DC voltage. It could also represent an AC voltage, just depending on what type of motor we have. And then there will also be some current I flowing into the motor such that our input power, PN, is simply the product of I and V. Now our motor will have some sort of shaft, which I am going to represent by this straight line here. And this shaft is connected to our mechanical system. Which will be considered the output or the load. So, let me write here, shaft. So, if we supply electrical power to our motor, what we're going to see is that our motor will rotate with some angular velocity omega, and that will in turn develop a torque, capital T, oriented in the same direction as the rotation, and our output power is simply our torque times our angular velocity omega. So we have an electrical power as our input that is converted into mechanical power at our output by our motor, which is serving as an electromechanical energy conversion device. In an ideal system, all of the input energy would be delivered to the output. However, in a real system, the efficiency is never 100%. And so we're going to figure out why this is by looking at the energy conversion process. So on our input side, we have our electrical system. And here in the middle, we are going to have our coupling. This could be an electric field or a magnetic field. In our class, we're going to be dealing principally with magnetic fields. And the reason that we're dealing with magnetic fields as our coupling fields is because it's going to allow us to develop a torque without any sort of physical contact being made between our systems. And then way over here on the right-hand side, we have our mechanical system like so. And then here is our output, which is some form of mechanical power, right? We have these three main components of our electromechanical energy converter: the electrical system, the coupling field, and the mechanical system. So we can see that, put extremely simply, the electrical input energy will be equal to the energy stored in our coupling field plus which means the output energy will literally always be less than the input energy because we have an energy storage medium effectively in the middle that's going to take some of our input energy away. This energy storage in the coupling field effectively sustains the energy conversion process. So it's really critical to our system to have it. Now, in a practical system or a real life system, there are also going to be losses that occur throughout the energy conversion process. So I'm going to put over here plus energy losses. And we are going to add these losses to our diagram. So the first loss that we're going to consider is electrical losses. Electrical losses are the I squared R losses or heat losses due to current flowing in the windings of the energy converter. The next loss that we are going to see are our field losses. So our field losses are, putting it in terms of stuff that we've talked about before, the losses that we observe in our core due to the changing magnetic field experienced by the core. So this could be eddy current losses. It could also be the hysteresis losses or some combination of both, right? So these are core losses due to changing magnetic field experienced . by the core. I'm going to put here eddy and hysteresis, like we talked about at this point well over a month ago. And then lastly, we have mechanical losses. Where our mechanical losses are the friction and windage losses due to the motion of moving components. So effectively, we're always going to lose some small part of our mechanical output due to the heat generated by moving things around, right? So including these losses and rearranging, we can rewrite our energy transfer equation as follows. So on the left-hand side, we're still going to have energy. And we're going to take away from this our I squared R losses so that we have some net electrical energy on the left-hand side of our equation. This will be equal to the energy stored in our coupling field plus our core losses. And then to our net field energy, we will have our mechanical energy, which is the mechanical output energy. So over a very, very short time interval, dt, we can express this as the following relationship. So we have a differential electrical energy, dWe, will be equal to WF plus some differential mechanical energy, dWm. Now, I think at this point, we all have a pretty good understanding of the electrical energy because you've taken multiple classes like your circuits class and then the first power class, which had a lot to do with electrical systems and power and energy today. Tell me if I'm going too fast, please. So the first thing that I want to talk about is the field energy. And so to discuss the field energy, we are going to look at a simple electromechanical, also known as a, you all should have some limited amount of experience with. Okay? I'm going to draw my core structure first. So I'll put it over here. my electrical system. I'm right now assuming it's going to be a DC voltage. Coil or our winding, which I'm going to draw now. So we have the relay like so. Now I'm complete. And this is going to be our voltage drop across our coil. E, where I'm using E for EMF like we did with transformers and all of that kind of good stuff, because it is literally the same thing. It's just an induced voltage. On the right-hand side, I'm going to draw the rest of my mechanical system. So I'm going to connect this plate to a spring. I'm going to write under here, spring, so that you know it's not an inductor. And then I'm going to give myself some anchor right here, which is just some fixed position. And so this is going to be my x-axis. So effectively positive x means that vertical plate is moving closer to the left-hand side, and the negative x direction would mean our plate is moving away from the left-hand side. And this is going to be just our simple reference position. Let's see here. Our coil has N turns. I have an air gap here, L sub G, like so. And if I'm carrying a current in my coil, I should have some flux as well. So let's go ahead and represent that on our picture like so. Found our flux path. Like so. And just for clarification's sake, we're going to say that that horseshoe-shaped bit is going to be completely stationary. So this is the stationary part of our energy conversion device. And then this plate, since it's connected to a spring, is the movable part of our energy storage device. So let's first consider a system that is at equilibrium, meaning is not moving. So if our movable part isn't moving, let me write this down. Then be 0. And our field energy So if we look at our diagram, we can see that our electrical energy is just going to be the voltage drop across our current flowing through our coil, I, multiplied by some differential time element dt. And once again, this will be equal. the voltage drop across our coil is related to the flux linkage in the system, which is a relationship we've talked about previously. E is simply equal to the derivative of our flux linkage with respect. And from this, we can say that our electrical energy is the derivative of our flux linkage with respect to time, multiply differential time element dt, and the two dt's are going to effectively cancel each other out. We can simply sides. So flux linkage. Okay. So I'm going to draw a picture here or a plot here that's known as a flux linkage current curve. So I'm going to put flux linkage on my vertical axis. I'm going to put current on my curve that looks something some particular air gap value changes, this graph is going to change slightly, okay? So the first thing that I want to do is actually talk about where we've seen effectively this exact same graph before, okay? So do any of you guys recall BH curves, right? So that's the relationship between the magnetic flux density B and the magnetic field strength H. I'm going to draw that graph over here in blue. On this axis, H on this axis. For that our flux link N times our magnetic flux. And our magnetic flux can be expressed as our MMF. So I'm going to have N. So MMF divided by equivalent reluctance, where MMF is N times I, and our equivalent reluctance is going to be the length of our core material divided by the permeability of our core material times the area of our core material. I'm going to rearrange this ever so slightly. So this is going to look like N times N is N squared. A is a constant. Our flux path length is a constant. And then we have I times mu, our permeability. Well, recall that mu is just the ratio of B divided by H. So our relationship between our flux linkage and I is directly proportional to the relationship between B and H, which is why these curves look so incredibly similar. Okay, so just trying to tie this stuff back to things that we've talked about before. All right, so going back to our graph, our differential field and so everything up particular is what's called our field energy. Something kind of interesting here. Everything below this curve is what's called our co-energy. Now, co-energy is literally using it because sometimes it's easier to find the energy of a system, and these two quantities are related. So our co-energy has the symbol WF prime. So it's almost the exact to current. While we're working on this relationship right here, let's talk a little bit more about these flux linkage current curves. So hopefully it's fairly obvious that these curves depend on the BH characteristics of the medium that we have, which I've already talked about. And it's also, okay. So if we were to plot these gamma I curves, or these flux linkage current curves for a particular material, and we varied the air gap length, we'd wind up getting a set of curves that look something like this. So one particular air gap length, LG1, if we made that gap length larger, than that, it's going to wind up actually looking kind of linear. So the direction here is increasing gap length. The relationship between our flux linkage and current becomes more linear, which inherently means that our relationship between our B field and our H field also becomes linear. And this is actually something that we talked about with an example problem when we were looking at BH curves and air gaps and inductance. We said that the air gap tends to linearize the inductance, and that linearization of the inductance is literally linearizing the relationship between flux linkage and current. All right, so if we have a system F our field energy, half the base, which is our current, times the height, which is our flux linkage on our graph. Now we can actually take this one step further, right? So our flux linkage is our inductance, right? So this over here, let's do this in green, right? So let me think about things really quickly here. Inductance is the number of turns divided by the equivalent reluctance of something, right? Well, the equivalent reluctance is related to our flux linkage. Let me put this here. So let's see, our flux times our flux. And so our flux is N times Ni over Req, or substitute that in here for a linear half our current. And then we're going to have this thing right here is we're going to have I squared times L, our self-inductance. So in a linear system, inductor. Once again, just tying all this stuff back to things that we've seen before. So looking at our magnetic circuit, just a couple of relationships that we've dealt with before. We know that our MMF, the number of turns times the current in our winding, and this is also equal to our magnetic field strength dotted into a differential line element. These are relationships that we dealt with on literally the first day of class. And I'm going to rearrange this to find our current is then the integral of H dotted into dl divided by our number of turns N. We also know that our flux linkage is N times our magnetic flux is simply our magnetic flux density, B. So from this, we can say that flux linkage is going to be N, which is a constant, times A, which is a constant, times some differential magnetic flux density B. That's the only thing that can change, so that's what we're going to have. And using these relationships, we can find for a generic system, our field energy is the integral from 0 to our flux linkage of I times the derivative of our flux linkage, which is going to be the integral of the line integral of h dotted into dl divided by n multiplied n's this is going to look like the magnetic plus the magnetic field strength in our air gap times the length of our air gap times area times our differential magnetic flux density. And then we can express our field strengths, HC and HG, in terms of our flux density. So that's going to be the integral of the magnetic flux density in our core divided by the permeability of our core into two integrals. Integral of BG divided by mu naught of Can you guys hear me?
Yes.
Okay, I don't know why, but here over the last couple of minutes, I've been kicked off of Zoom like 3 times in a row. Let me try to start sharing my screen again and hopefully it doesn't kick me. All right, did not get kicked off after trying to share my screen this time. What was I've done a lot of math, but I don't know when I got kicked off of Zoom the first time. Um, so ballpark, where were we at?
You were still writing that second line there that's on your screen.
This one right here that I just underlined.
Yes.
Okay, so what I did for this particular line was simply recall that the magnetic field intensity H is related to the magnetic flux density B by the relationship. Let me put it out here in blue. Um, B is equal to mu times H, which means H is B over mu. So I substituted that relationship in, and then I also distributed the cross-sectional area A. So in my first term, I have AC because I'm dealing with the area of my core. And the second term is all about what's going on in my air gap. So I'm using AG, which is the cross-sectional area of the air gap. I then split my integral up into two integrals, which is the line directly below. And then I'm actually performing that integration in the bottom line. So the integral of b with respect to b is just 1/2 b squared. And so all of my constants are just getting carried through. And so over here on the right-hand side, this is going to be the integral of my flux density in my air gap. So that's going to look like bg squared over twice mu naught times LC times AC. And so now let's talk about what these things represent. So this bit right here is effectively the energy density, so the energy per unit area of the core. And this term right here, LC times AC, is really just the volume of the core, which I might use, so I'll call that VC. And then we have something similar over here on the right-hand side. We have the energy density in the air gap. And then we have the volume of the air gap, which I might call V sub G. So the field energy then is some combination of the energy stored in our core material and the energy stored in our air gap. And so what I would like us to do is work a numerical example to kind of see what shakes out of this. So we're going to use our relay circuit from before, and I'm going to give our structure dimensions. So let's do that really quickly. So this is our core structure. Or something similar to it. So let's say that this distance is 5 centimeters. This distance is 5 centimeters. This distance is 10 centimeters. This distance is 10 centimeters. This is 5 centimeters like so. And this guy right here is also 5 centimeters. And then the distance from here to here is my gap length. And I'll just write this out. So let's say that LG is 5 millimeters, or half a centimeter. Before we get into the other details, because we're going to wind up using our core length, our gap length, our core area, and our gap area, and all of that kind of stuff, let's go ahead and calculate those really quickly. So what should the cross-sectional area, oh, and let's say that the thickness is also 5 centimeters. So what should the area of my air gap be? It'll be the height of 5 centimeters plus a gap length times the thickness of 5 centimeters plus a gap length. So that's going to look like 5.5 centimeters quantity squared, which comes out to be 30.25 centimeters squared. And then the volume of our air gap is then the product of our gap length and our gap area, which comes out to be 30.25 centimeters cubed. Actually, I'm missing something really quickly here. Let me sneak it in. Sorry about this. I'm putting this factor of 2 out front because there's 2 air gaps. So this VG effectively is the total air gap volume. So the volume of both gaps added together. And since they both have the same length and the same cross-sectional area, I'm just going to be lazy and just multiply the volume of one by a factor of 2. Our flux path length, or our core length, is going to be this length that I'm doing in light blue. And so that's going to look like 4 times 10 centimeters plus 5 centimeters comes out to be 60 centimeters. The area of my core is just 5 centimeters squared, or 25 centimeters squared. And so from this, the volume of my core comes out to be 1,500 centimeters cubed. So before we move on from here, I just want to point something out that's actually kind of obvious. The volume of our core is way, way, way larger than the total volume of our air gap. Okay. All right. So now getting into the circuit details as well. So let's say that our coil had 250 turns. Our core has a permeability of 5,000 mu naught, and the resistance of our windings is 5 ohms. So I want us to determine the DC voltage needed to establish a magnetic flux density of B is equal to 1 Tesla and B the energy stored in the coupling field. So for part A, this is largely the same stuff that we did at the beginning of class, right? So effectively, let's talk our way through how we might calculate voltage in this system, okay? So our DC voltage in this system should be whatever DC current is flowing in our system times that 5 ohms of resistance. Okay, just good old Ohm's law, nothing remotely fancy here. In order for us to calculate the DC current flowing in our system, we are going to use Ohm's law for magnetic circuits. And so that's going to be our magnetic flux times our equivalent reluctance divided by our number of turns. Now, because we've done calculations like this so many times, I'm going to go through this pretty quickly so as to not bore you. Our equivalent reluctance would be our core length divided by our core permeability times our core area. So that's the reluctance of the core. And then I'm going to have 2 air gap reluctances to take into account. So that's where this factor of 2 comes from. So the gap length divided by mu naught Ag. We already know what numerical value all of those different things has. And so this comes out to be 2.669 times 10 to the 6 amp turns per Weber. Our magnetic flux is simply the magnetic flux density in the core, B sub C, times the area of the core. I'm going to do this one out just really quickly, just so that the units are taken care of. So 1 Tesla is 1 Weber per meter squared. Our core area is 25 centimeters squared. I'm going to multiply this by a conversion factor of 1 meter per 100 centimeters quantity squared. And this comes out to give me 2.5 milliweber, or 2.5 times 10 to the minus 3 Webers. And using this, our DC current is 2.5 times 10 to the minus 3 Webers times 2.669 times 10 to the positive 6 amp turns per Weber divided by our number of turns. And this gives us 26.689 amps. And therefore, our DC voltage is 26.689 amps times 5 ohms, comes out to be 133.443 volts. So it requires us to apply 133 and some change volts in order to establish a magnetic flux density of 1 Tesla in our core and air gap respectively. Okay. So nothing real fancy there. We're going to use this as a point of comparison here in a couple of moments. For part B, calculating our field energy, our field energy is the flux density in our core divided by twice mu c times the volume of our core plus flux density in our gap squared divided by twice mu naught times the volume of our gap. I'm going to write these out really just to show you how the units work out here. So in my denominator, I'm going to have 2 times 5,000 times 4 pi times 10. So in our previous examples, when we were calculating reluctance, I always use 4 pi times 10 to the minus 9 henries per centimeter. Because we have something that's in Tesla or in Webers per meter squared in the numerator, I'm going to choose to express this as 4 pi times 10 to the negative 7 henries per meter, just to get away from having to do an additional unit conversion here. Okay. So I just wanted to be clear about that. Actually, let me go one step further here. So a Henry is a volt second per ampere. So I could write this as volt seconds per amp meters, which will help us cancel things out here in a moment. Up here in the numerator, I have 1.0 Tesla, where a Tesla is a Weber per meter squared, and a Weber is a volt second. So I have volt seconds per meter squared. This is squared. Now I'm going to multiply this by my volume, 1,500 centimeters cubed, and then a conversion factor of 1 meter per 100 centimeters. That's cubed. Let's look at what the units are doing here, just for the sake of argument. So I'm going to have volt squared times second squared divided by volt seconds. So that's going to give me some units of, let me just put them over here. So I have volts seconds in the numerator. These centimeters are going to cancel these centimeters cubed. So now I have meters cubed in the numerator, and then I have a meter squared and a per meter down here. And so all of these meters are going to cancel each other out. And the last thing that I need to pay attention to is I have 1 over amps. So that's going to put an amp up in my numerator. So I have volts times amps, which is watts times seconds. Watts times seconds gives me a number in joules. Just showing you how all of the units work out. Because I have energy, my expected answer should be in joules. Doing the same thing over here, 4 pi times 10 to the minus 7 volt second per amp meter. Sorry, there should be a factor of 2 there that I missed. Let's see, 1.0 volt seconds per meter squared, quantity squared, 30.25 centimeters cubed, and then 1 meter per 100 centimeters, quantity cubed. The units all cancel out the exact same way. This is going to wind up giving me, so my contribution of the energy stored in the core is 0.119 joules. And then the energy stored in the air gap, it's actually going to come out to be 12.036 joules. So about 99% of the energy stored in this system, or our field energy, is stored in the air gap. And the total, for what it's worth, is 12.155 joules. So realistically, we could have neglected the energy stored in our core and lost effectively next to no information whatsoever about what our field energy is doing. That is because our air gap linearizes all of our relationships, right? So effectively, our field energy is just linearly dependent on our air gap volume in this case. All right, so there's field energy, just simple energy storage, all that kind of good stuff. Now let's talk about mechanical energy and force. And this is going to be a little esoteric at first, and then we'll tie things back up. So, revisiting our relay system, what we're going to do now is we are going to consider what happens if we let the movable part actually move. And so we're going to allow it to move from one position, which we'll just call X1, to another position, X2. And the result of that movement is that the air gap will have decreased at the end of the movement, right? So if we plot the lambda I curves for both of these different air gap lengths, it's going to look something like this. So here's lambda on our vertical axis. Here's I on our horizontal axis. And I'm going to have two curves, one like this, corresponding to x is equal to x1, or our original gap length. And then another curve that's going to be higher, corresponding to x is equal to x2, where we have our smaller gap length. Okay. So if the movable part has moved slowly, the current should remain constant during the motion. So let's say that our current is here, right? This is what our constant current is. So originally we were at this operating point, which I'm going to call A. And now we're going to be at this operating point, which I'm going to call B, because our gap length has changed. And these points have corresponding flux linkages, flux linkage 1 and flux linkage 2 on our graph. I'm going to call this point C and this point D. And then down here at the bottom left is my origin, which I've labeled as O. So, I'm just going to say here explicitly, the operating point of the system has moved from A to B on the lambda I curve due to the motion. So during the motion, we must have had some change in electrical energy to cause said motion, right? Effectively, since our flux linkage has changed, our voltage has changed, and since our current was constant and we have some voltage, we should see a change in electrical energy. So that's going to be dWe is equal to the integral of EI dt, or the integral from flux linkage 1 to flux linkage 2 of I d lambda. And this is literally just the area mapped out by the shape A, B, C, D. So this little rectangle right here. Okay. The field energy in the system has also changed, right? So our field energy is going to be effectively the area from the origin to BC. So this area is the energy after our plate moved, and we're going to subtract from that the area OAD, which is the energy before our plate moved. Okay. Using these two results, our mechanical energy is then the difference between our electrical energy and our field energy, which is the area of rectangle ABCD minus the area from the origin to BC minus the area from the origin to AD. And this is the area from the origin to AB. So I'm going to color that in here. So this is our mechanical energy, the area that's bounded by those two lines, okay? This is an increase in the co-energy of the system, right? So if the co-energy is defined as the area under our curve with respect to the horizontal axis, then this area right here is an increase in co-energy because it's getting larger. So we can say that our mechanical energy is the same as the increase in our co-energy. So mechanical force Fm, so if Fm is the mechanical force that causes, the displacement from x1 to x2. So let's say that our change in x is x2 minus x1. Then our mechanical energy is simply our force times that displacement, which is the same as the change in our co-energy. So if we rearrange this relationship, what we'll find is that our force is the partial derivative of our co-energy as a function of current and displacement. And we're going to take that partial derivative with respect to our displacement while we hold our current to be constant. So this is what it looks like when we move our plate very slowly. This is what the relationship for our mechanical force is. Now, let's go the other way around, and let's say that our plate moves very, very fast. So for a fast movement, the flux linkage is effectively going to remain constant during the motion. So if I plot things out here again, where this is lambda, this is I, and I once again have two curves. X is equal to x1, x is equal to x2. The flux linkage does not change during the motion. So effectively, here is our flux linkage. We're going to have some operating point A here, where we started from, and this should be the same as the A earlier. It's corresponding to some current I1. And then since our flux linkage didn't change, here's our new operating point, which I'm going to call P. And it has some corresponding current I2. So we can see that the operating point of the system has moved from point A to point P on the lambda I curve. Well, what's the consequence of our flux linkage remaining constant? Well, if our flux linkage is constant, then the derivative of our flux linkage is zero, which means our electrical input energy didn't change, right? So if our flux linkage is constant, then d lambda is equal to zero, and dWe is equal to I d lambda is zero, right? So that means that effectively the field energy is what's causing this movement in this case. And so we should see that dWf plus dWm is zero, which in turn means that our mechanical energy is equal to negative the change in our field energy. So effectively, our mechanical energy here is this area that's shaded in from the origin 0 to A to P and back to the origin. And it represents a reduction in our field energy, which makes sense. If it's not the input energy that's causing the movement, then our stored energy has to decrease in order for the mechanical energy to increase. Okay. From this, our force, Fm, is going to be and I'm putting in absolute value signs effectively just to get rid of that negative sign. So before we saw FM was a mechanical force was a positive thing caused by the increase in electrical input energy. Now, or excuse me, the increase in co-energy. Now we're seeing our mechanical force is due to a decrease in field energy. And because I don't want to have to worry about the signs, I'm just putting absolute values here. And so this is going to be the change in our field energy as a function of flux linkage and position with respect to position, where our flux linkage is constant. In a linear system, where our field energy and our co-energy are the same thing, effectively that means that we're going to get the exact same result regardless of how we look at this thing. So if we go back to our relay system, what we'll find is that our mechanical force, Fm, is the derivative of either our field energy or our co-energy. Since we already have an expression for our field energy, let's use that. So what's the thing that's changing in our system? What's the gap length? So the gap length Lg is just taking the role of x, our displacement, in our generic equation. And so we're going to have the derivative with respect to gap length of our expression from earlier, our magnetic flux density squared divided by twice mu c times AC LC plus our magnetic flux density in our air gap twice mu naught AG LG. And the derivative of this first term is just derivative of a constant, so it's 0. And so this winds up being BG squared divided by twice mu naught times the area of our air gap. So we can see that only the energy stored in the air gap contributes to our mechanical force, which is pretty great because, as we saw earlier, the overwhelming amount of the stored energy is the energy stored in the air gap. The core, or the energy stored in the core, contributes practically nothing. Okay, so as a quick example, let's calculate the force acting on the movable plate from our previous example, right? So our mechanical force, Fm, is flux density in our gap twice mu naught Ag. So that's going to be 2 times 4 pi times 10 to the negative 7 volt seconds per amp meter in my denominator. And then I'm going to have 1 volt second per meter squared, quantity squared, 30.25 centimeters cubed, 1 meter per 100 centimeters squared. Sorry, this should be 30.25 centimeters squared because I'm using the area. And this comes out to be 1,203.609 joules per meter, which is the same thing as a Newton. And this is the force per air gap. So over 1,000 newtons of force is acting on our movable plate due to the energy stored in each of the air gaps. So that's a very, very strong attractive force, which is exactly what we want because this is a relay. We want effectively it to snap closed, right? As an aside here, I want us to work another example. So I want us to calculate the average or RMS force acting on the movable plate if a 120 volt RMS at 60 hertz voltage is supplied by the voltage source. Okay. So in the first example, we found out that a DC voltage of 133 volts and some change was necessary to establish a magnetic flux density of 1 Tesla in our air gap, and that 1 Tesla of magnetic flux density correlates to a force of 1,203 newtons per air gap when we have a gap length of 5 millimeters. Now, all of the other conditions are the same, right? Our gap length is still 5 millimeters, but I want to see what happens if instead of applying a DC voltage, we apply an AC voltage that's comparable in size, right? So 133 volts DC and 120 volts RMS, they're not the same, but it's fairly close. Okay. So under AC excitation, coil will have an impedance of Z is equal to R, 5 ohms from before, plus J times omega times the coil's inductance value. The coil's inductance value, L, is the number of turns squared divided by the equivalent reluctance. So that's 250 turns squared divided by 2.669 times 10 to the 6 amp turns per Weber. And this comes out to be 23.418 millihenry. And from this, our impedance is 5 plus J 8.828 ohms, or 10.146 angle 60.475 degrees ohms. Our RMS current flowing in our coil is going to be the RMS voltage divided by the magnitude of our impedance. So this is 120 volts RMS divided by 10.146 ohms, which comes out to be 11.827 amps RMS. So if I'm not mistaken, earlier we wound up having something like, I think it was in the ballpark of 25 amps flowing in our coil. By applying an AC voltage, we actually see that our current is reduced to a little less than half of what it was previously. So since our current is smaller, we should expect to see that the B field in our relay is also smaller, right? So using Ohm's law for magnetic circuits, we could find that the RMS value of our magnetic flux density is going to be N times our RMS current divided by our core area times our equivalent reluctance. So that's going to be 250 turns times 11.827 amps RMS divided by 25 centimeters squared times 2.669 times 10 to the 6 amp turns per Weber. And actually, I'm going to put a conversion factor here really quickly. If we look at these units, so here's amps over amps, here's turns over turns. So right now, effectively, we have Webers per centimeter squared, and I want magnetic flux density, which is measured in Tesla or Webers per meter squared. So I'm just going to tuck in a conversion factor here of 1 meter per 100 centimeters quantity squared. And so that's going to get rid of my centimeters, leaving me with Webers per meter squared or Teslas. And we get 0.443 Tesla. So because we are using an AC system and our coil now has some reactance, we see that our magnetic flux density has gone down by a little over a half, which makes sense because our current went down by a little over a half. Using this, the RMS force, which is just going to be the average force on our moving plate, is going to be the RMS value of our flux density squared over twice mu naught times our gap area. And this comes out to be 533.390 newtons. So using a comparably sized AC signal at 60 hertz results in less than half of the force being applied to our moving plate, which is why, typically speaking, when we're trying to have linear movement, like in a relay, we usually use DC voltages and currents because the force is significantly higher, or to think of it in a different way, we can achieve the same amount of force using a much smaller voltage. All right, so I promise I'm almost done ranting at you guys for today. So everything that we've done to this point has described how energy is converted into a linear displacement in an electromagnetic system, which I personally find very interesting. However, the overwhelming majority of electromagnetic energy converting machines actually produce rotational motion. So we are going to use the results that we've done here for linear motion and apply them to a rotating system. So let's look at rotating machines. So the first thing that I'm going to draw is a simple representation of a rotating machine, and it is actually incredibly similar to our original circuit, as it were, containing the relay. So I'm going to have a core material. With an air gap. And I've drawn that little thing with a curve in it, and you'll see why in just a moment. And then this circle here in the middle is kind of like a pin. So we're going to have something that rotates, and this is our point of rotation. And then my rotating thing is going to be over here. Like so. I'm going to define a couple of axes here because they are important. So this dashed line right here represents our stator axis, which means this structure right here is what's called the stator. And then this dashed line right here represents the rotor axis, which means this structure right here is what's called our rotor. And the stator is the stationary part of a rotating electromagnetic machine. And the rotor is the rotating part or the movable part in a rotating electromagnetic machine. So it still has the same basic structure. There is a stationary part and there is a movable part. But now instead of having linear motion, we're having rotational motion. So our rotational motion is going to be characterized by some angular frequency, omega m. And then we're going to define our angle theta as the difference between our stator axis and our rotor axis. We should have axis here. So theta is constantly changing as our rotor spins. Now, this is the physical structure. Now let's put the electrical structure in here, right? So we are going to have a coil on our stator. Where we're going to carry some current IS, that is our stator current, and we might also have some stator voltage ES. And then depending on the type of machine that we have, we may also have a winding on our rotor. Where this will be our rotor current IR. and our rotor voltage ER. It's not required for us to have coils on both parts, okay? So really, we could actually just look at this particular diagram and classify a bunch of different types of electrical machines. So for example, if the voltage that's applied across our stator terminals is an AC voltage, and we induce an AC voltage in our rotor, that's what's called an induction motor. If we apply an AC voltage to our stator and apply a DC voltage to the coil on our rotor, then we have what's called a synchronous machine. If we apply an AC current to our stator and we don't have a rotor coil at all, then we have a reluctance motor, which is actually the type of motor that Tesla started using within the last couple of years for their drivetrains on all their electric vehicles. If we had a DC current flowing in our stator windings and we had a few other parts like a commutator and stuff like that, this would be representative of a DC motor. So this basic format is actually how all of the different electric machines that we're going to analyze for the rest of this class, how they're generally laid out. So the stored field energy in the system dWF is going to be the stator voltage times the stator current times some differential time element dt plus the rotor voltage times the rotor current times some differential time element dt. And because we know that the voltage is related to the flux linkage, we can express this in the same form that we did earlier. So this will be IS times D flux linkage S plus IR times the rotor's flux linkage. For a linear magnetic system where we have coupled coils, which is something that we have right here, our flux linkages are going to be expressed in terms, or can be expressed in terms of the self-inductance and mutual inductance of our coils. Okay? So our flux linkage for our stator is going to be the self-inductance of our stator, which depends on the value of our angle theta times IS plus the mutual inductance between our stator and our rotor, also dependent on angle theta, times IR. And then the flux linkage of our rotor is going to be the self-inductance of our rotor, which is dependent on theta, times IR, plus the mutual inductance, still dependent on theta, times IS. So I'm going to ask you guys a question. I hope somebody at least volunteers to try to answer it, but it's okay, I guess, if you don't. Why do you think the self-inductance and the mutual inductance in this system depends on that angle theta? Anybody care to venture a guess? All right. So what's happening to the air gap length as that rotor spins? It's constantly changing, right? So when the rotor and the stator axes are in perfect alignment, meaning theta is equal to 0, the air gap is at its minimum, right? Which means our self and mutual inductances should actually be at their maximum values. As the rotor spins, that gap length is going to constantly change. And because that gap length is constantly changing, the self-inductance and mutual inductance values are also constantly changing. Okay. So if we substitute in these relationships for our flux linkages, what we'll find is that our field energy is equal to IS times the change in LS as a function of theta IS plus MSR as a function of theta IR plus IR times the change in, excuse me, LR as a function of theta times IR plus MSR as a function of theta times IS. And this can be written as LS as a function of theta times IS, the derivative of IS, plus LR as a function of theta, IR, change in IR, plus MSR as a function of theta times the change in the product of IS and IR. And so our field energy is just going to be the integral of this thing. So that's, sorry, LS as a function of theta times the integral from 0 to whatever our stator current is of our stator current with respect to our stator current plus LR integral from 0 IR of IR DIR plus MSR integral from 0 to ISIR of the change in IS times IR. And this comes out to be 1/2 times the self-inductance of the stator times the stator current squared plus 1/2 times the self-inductance of the rotor times the rotor current squared plus a whole mutual inductance times the product of IS and IR, right? So this equation should actually look pretty familiar to you guys as well. We didn't cover it in this class, but we covered it in ELET 280. This looks extremely similar to the energy stored in a transformer, where we have some energy stored in the first coil, some energy stored in the second coil, and then some energy stored because of the mutual inductance between the coils. It's the exact same situation here, but now our self-inductances and our mutual inductance, which I forgot to put the dependency on theta, so let me sneak that in here, matter. All right, so the torque that's developed in a rotational electromagnetic system is analogous to the force that's developed in a linear electromagnetic system. So for our linear electromagnetic system, our mechanical force was the partial derivative of our field energy with respect to displacement. So in a rotational system, our torque is going to be the partial derivative of our field energy with respect to our angle, where our current is held constant, which comes out to be 1/2 IS squared times the derivative of our stator self-inductance with respect to theta plus 1/2 IR squared times the derivative of our rotor self-inductance with respect to theta plus IS times IR times the derivative of our mutual inductance as a function of theta with respect to theta. And these two terms right here are what are known as the reluctance torque. And they are caused by the variation in the self-inductance due to a changing rotor position. And then that last term, it doesn't have a special name, but I'm going to call it the developed torque, is due to the variation in the mutual inductance seen between the rotor and the stator. So in class on Tuesday, because I talked too damn long, I'm going to wrap this lecture up by talking about a special case of a rotating machine, which is a cylindrical machine. And this will be our bridge into our formal discussion of induction machines, synchronous machines, etc. All right, so thank you guys for putting up with me for the last 2 hours, especially because of the technical difficulties and all that kind of stuff. I will see you guys on Tuesday. Have a good weekend.